Here, I'm presenting learning from synthetic animals. In this talk, I will show you how we can combine animal CAD models and unlabeled real images to train a neural network that allows for accurate 2D pose estimation on real images. Despite great success in human 2D pose estimation, progress for parsing animals is still limited by the lack of large-scale datasets. So why don't we just annotate large-scale animal datasets? First, for animals, it's impractical to annotate all animal species. In addition, it's hard to annotate various ground truths, particularly for those in 3D. Therefore, we propose to use CAD models to address the problem. There are two types of CAD models available: realistic models and low-cost models. Realistic models are expensive and come with less domain gap. In comparison, low-cost models look less realistic and come with a larger domain gap. In this project, we choose to use low-cost CAD models. However, since low-cost CAD models are with limited realism and limited diversity, we need to develop an efficient algorithm to bridge the domain gap. We propose to use both domain randomization and semi-supervised learning to address the challenge. I will first introduce how we generate our synthetic animal dataset. Given a CAD model along with a few animation sequences, we can render an animal with a bunch of random parameters. For each rendered image, we also generate rich ground truth, including depth maps, part segmentation, and density points in both 2D and 3D. After a synthetic animal dataset is generated, we can employ semi-supervised learning to take advantage of both synthetic images and unlabeled real images. Our idea is to bootstrap weak models trained on synthetic data with unlabeled real images. Given a synthetic dataset, we first train a weak model F, then we can generate pseudo-labels Y hat for real images. To generate pseudo-labels, one straightforward idea is to use model's confidence score as a proxy of correctness measure, and then apply thresholding to identify the set of labels used for training. However, this is less ideal since weak model's prediction is noisy and it can always reinforce its own errors. So we propose to use consistency check to generate high-quality pseudo-labels. We propose 3 consistencies, and I will introduce them one by one. Given an image X, we can apply transformations that do not change key point locations, such as color perturbation and Gaussian blur. Under this scenario, the generated prediction on transformed images should be consistent with the predictions of the original image. We call this invariance consistency. Similarly, we can apply another set of transformations where the image and key points are transformed equally, such as random rotation and scaling. We refer to this consistency as equivariance consistency. When videos are available, we can further approximate the transformation between 2 consecutive frames by optical flow and apply temporal consistency. We can jointly apply all 3 consistencies and ensemble all predictions together to refine the weak model's prediction. In practice, we simply generate pseudo-labels and train our weak models in an iterative fashion. After n iterations, we can obtain a strong model Fn. Then I'd like to discuss some results. Here shows a high-level overview of our experiments. We observe that our algorithm generates accurate predictions for animal 2D poses. The trained model also demonstrates better generalization on the viral domain adaptation challenge dataset. We also try a multitask learning setting to show we can train key points and semantic parts jointly. We employ the original stacked hourglass model as our backbone and train a separate model for each animal category. On the right, we show our 2D pose estimation results on the tick-dot dataset without using any real image labels. We also quantitatively evaluate the 2D pose estimation. In both settings, our models achieve better results. Our approach is also easy to extend to other animal categories and rare key point configurations. You can see we can also predict the key points of elephants' trunks. We demonstrate our trained models can also generalize well on different domains on the viral domain adaptation challenge dataset. We also modify the original stacked hourglass architecture to enable multitask learning. We demonstrate models trained in this way can predict semantic parts reliably using just the synthetic images. We also have our dataset and code publicly available, so please check the website if you're interested.